Hey everybody, in this last and final video lesson of this chapter, we're going to discuss a topic called net ionic equations. Now, I'm going to spend the first part of this talking about what is a net ionic equation and talk about a specific situation about chemistry that's happening in solutions. Now, the reaction types that we just learned about in our video lessons, of the 5, the double displacement reactions are the ones that happen most in solutions. And so net ionic equations are going to be applied to just double displacement reactions in our chemistry course. But keep in mind, if you decide to take an advanced chemistry course next year, you might learn about net ionic equations again, and they can be applied to things that are not double displacement. First, let's talk about what's actually happening inside a beaker when a solution is made. Now let's pretend you have a beaker down here, and in that beaker you have maybe 50 milliliters of water. Now you're going to take a solid ionic crystal, and we're going to call that ionic crystal substance AB. Now a solid AB is connected to each other using ionic bonding, and so the ionic bonds are very obvious. But when you put the solid into solution, the ionic bond breaks easily in water, and so A is no longer touching B, but rather you have just A ions and B ions floating around in solution. Even though we might call it aqueous AB, in truth, the solution of AB just consists of individual A ions and B ions floating around in the liquid. At this time, I'm once again going to splice in another video clip that I've created for another chemistry course. And in this video clip, I'm going to explain how these ionic solutions, when mixed together, can result in a net ionic equation. And at the end of this video, I'm going to come back to this and summarize what we learned and finish up the video at that time. Now let's talk about net ionic reactions and how we get to that point. You will start with a chemical reaction. That's the full reaction. That includes the states of matter. And you have to decide which of the ions on the reactant side and on the product side start as aqueous and end as aqueous. Because if they start and end as aqueous, then they are considered spectator ions. And we talked about that a little bit before. Ions not involved in the formation of a precipitate or a gas are called spectator ions. So we start with the full reaction, and we split the full reaction into the complete ionic equation, where it shows all the ions and their states of matter for the precipitation reaction. And then you make sure that you split any aqueous into ions, but keep any solids, liquids, and gases together for the complete ionic equation. Here's an example. See, we have 3 sodium hydroxides that are aqueous, and you have 1 aluminum nitrate that's aqueous, and that's going to produce 3 sodium nitrate that are aqueous and 1 aluminum hydroxide that's solid. This is the full reaction. Now let's translate that into the full ionic equation, and I'm going to do that in real time. So these are aqueous, and so I need to split them up into their ions, because it says up here that split aqueous into their ions for the full ionic reaction, or the complete ionic reaction as we call it. So we have 3 sodium ions, because the coefficient here in front of the sodium hydroxide is 3, so that carries through to the whole molecule. So I have 3 hydroxide ions that are also aqueous. Now a word of note, you want to give yourself lots of room or write really small when it comes to writing out the complete ionic equation, because you're splitting up all these ions and it takes up a lot more space than you do when you write the complete reaction, or when you write the full reaction, or even the net ionic. This is the most space consuming part of this process. So anyway, moving on, we've got aluminum, and there's only 1 molecule of that. So we've got aluminum, which is a +3 charge, and that's aqueous. And we've got 3 nitrate ions, because the little 3 behind the nitrate means that there's 3 of those ions. And so I need to account for 3 nitrates. Now I'm actually going to do this next part, the products, on a different line, because I know I'm going to run out of room. But on the product side, I've got 3 sodium nitrates, so that means I got 3 ions of sodium, and those are aqueous. And I've got 3 ions of nitrate, and those are also aqueous. And then the last thing I have is the aluminum hydroxide. Now I don't want to split this up into ions, because it says up here, split only the aqueous into ions, keep your solids, liquids, and gases together. So I'm going to just write AlOH3 with a solid without splitting those up into the ions. And now you have the full ionic equation, or sometimes referred to as the complete ionic equation, which shows all the ions in a precipitation reaction. Now from here, we cross out anything that is of the same state of matter on both sides of the reaction arrow. So for example, I start with 3 sodium ions on reactant side and 3 sodium ions on the product side. So those cancel each other out. Another thing I noticed is that I have 3 nitrate ions on the reactant side and 3 nitrate ions on the product side. And so those cancel out as well. I'm going to scroll up to give myself a little bit more room. But in blue, I'm going to write the net ionic equation now. And the net ionic equation is anything that doesn't get crossed out of the full or complete ionic equation. So I've got the 3 hydroxide ions. I've got the 1 aluminum ion. And then the only thing on the product side that didn't get crossed out was the solid product or the precipitate. And now I have the net ionic reaction that I got from the full ionic reaction. And this is the final answer. You'd be expected to write out the net ionic equation, and the full ionic equation is just an intermediate step. It's kind of showing your work. You'd basically be presented with a complete reaction and have to come up with the net ionic. And the complete ionic would be kind of this part in red, which is where you're showing all your work. Now the trained chemist eye can actually look at a overall full reaction and identify the aqueous that begin and end, and you can kind of fast track this process. But I highly recommend that you write out the full ionic, and in some cases the directions to the worksheet or the quiz will be write out the full ionic before you write out the net ionic. But if you were just asked to write out the net ionic, you're taking a risk if you don't show your work that you know what you're talking about. And so the final answer down here is what I'm looking for. But you definitely want to show your work if it indeed calls for it. One last word to note. Sometimes you may be asked, what were the spectator ions in this reaction? And anything that you crossed out in blue from the full ionic are considered spectator ions. And so in this case, the sodium ions and the nitrate ions would be the spectator ions. I want you to take a moment and pause the video and work this on a separate sheet of paper, and then I'll go through the answers with you. I need you to complete and balance a reaction. Then I need you to write out the full ionic reaction. Then identify what the net ionic reaction is, and then finally identify any spectator ions. So go ahead and pause the video at this time. I'll work out the answer, and when you're ready, go ahead and hit play. So the first thing I did was I exchanged the cations with one another, and so that the nickel was with the bromine and the potassium was with the nitrate. So I put potassium nitrate over here. And remember my solubility rules. All potassium and nitrate salts dissolve, and so this must be aqueous. The other combination of ions, nickel and bromine, neither of those are falling under my rules that I have to remember. It's not a potassium, sodium, ammonium, or nitrate salt, so it must be solid. So I know that this is going to be a solid compound. And then I went ahead and balanced the reaction. Now some students want to know, how did I know nickel was a +3 charge here? Well, if it's a +3 charge on this side, and I know it's a +3 charge because nitrate's always a -1 charge, and if I needed 3 -1s, then nickel must have been a +3 charge on this side. Now we don't include the charges in the actual reaction. I'm just writing them in there for context. But if it's a +3 charge on this side, it has to be a +3 charge on this side. And when it combines with bromine, which is a -1 charge, it has to be NiBr3. And then I go ahead and balance the reaction, and I get 3 KBRs on the left, and that means I have 3 KNO3s on the right. So now I have checked off number 1. I have completed and balanced the overall reaction. The next thing I want to do is take the overall reaction and write out the full ionic reaction. So here it is in blue. I took the overall reaction on the top, and I split up anything that was aqueous into its ions. And so 1 sodium plus 3 and 3 nitrate ions are right here, and then the 3 potassium bromides, potassium being a +1, bromine being a -1, and I put those right here. Now on the product side, I have another aqueous compound, so I split up those ions, 3 potassium ions and 3 nitrate ions that you can see right here. And finally, the solid, which I keep clumped together as a compound. I do not split that into its ions. And so now I've officially finished step number 2, which is write out the full ionic reaction. Now I show my work in green, and I cross out anything that's equal on both sides. So I've got 3 nitrates on the left and 3 nitrates on the right. I've got 3 potassiums on the left. I've got 3 potassiums on the right. And the only thing that's not left over is the nickel ion, the bromine ion, and then the nickel bromide. And so the net ionic reaction looks like this, which includes just the ions of the reactant side that didn't get crossed out and the solid precipitate on the product side. So I can check off number 3 and say that I've completed the net ionic equation. And finally, I'm going to identify the spectators. And as I mentioned in the last slide, the spectators are the things that you crossed out. So the spectators are the NO3 minus and the K plus are the spectators. As you just saw, net ionic equations result when ionic compounds that are separated into their ions in a solution is poured or mixed with another set of ionic compounds that have been separated into their solution, and some of those ions happen to find each other. And when they find each other, they precipitate or form a solid because they are insoluble. And the ions that do not precipitate just stick around. And to simplify the reaction, we don't write the ones that stick around, the ones in which we call spectator ions, but instead we only write the ions of the things that started out as aqueous but changed to solid as a product. And so when we rewrite the reaction, we show only the net ionic equation or the net ionic reaction. In other words, only what happens and doesn't show what doesn't happen. So I'm going to finish off this rather long video with one more example, and we're going to take this full reaction and break it down into its full ionic reaction. And then we're going to try and figure out which of them are spectators, cross those out, and finish with a net ionic. So let's take a look at this first one. I've got Na3PO4, and I've got 2 of those molecules. Now what's tricky about this one is, what do I do with the 2 molecules if there's 3 sodiums? Well, when I break this down into its ionic substances, since they're aqueous, then it's 2 times 3, or 6 Na ions, and 2 PO4, because the 2 applies to both parts of this ionic substance. And if there's already 3 sodiums, then 2 of the 3 means there's 6 sodium ions and 2 phosphate ions. And the ion phosphate is 3 minus. Now, the same thing applies for this next one. I've got 3 copper nitrate. So I got 3 copper ions, and then I have 3 times 2, or 6 nitrate ions, which are negative charge. Now, the copper charge I can figure out because I know nitrate's a -1 ion, and there are 2 of them, so that must mean that this copper is a 2+ charge. Now, on the product side, I have a solid here, and so anything that's solid, liquid, or gas kind of just stays together. You don't need to split those up, so I'm just going to put Cu3PO4 parentheses 2, and then finally I'm going to take 6 Na plus ions and 6 NO3 negative ions because that is aqueous, and aqueous splits up. Now in another color, I'm going to come in and I'm going to cross out anything that's the same on both sides. So I got 6 sodium ions here and 6 sodium ions on the product side. I've got 6 nitrate ions on the reactant side and 6 nitrate ions on the product side. And from there, the only things that I have left, I've underlined now in red. I've got 2 PO4, 3 minuses. I've got 3 Cu, 2 pluses. And I've got a Cu3 PO4 parentheses 2, and that is my solid. And both of these first 2 are aqueous, so I don't want to forget those states of matter. And in red, I have the net ionic equation. I write out the full ionic, cross out the spectators, and just write what's left, which is the net ionic equation. If there was a follow-up question that asks what are the spectator ions, it would be the ones you've crossed out. It would be the sodium ions and the nitrate ions. If you'd like to try this last one, go ahead and do it, but I'm not going to do it for you. That one's for you to try on your own. That takes care of this video lesson. Thanks for watching.